So this is the optimal change point detection tutorial session by myself and Toby. So I'm going to be doing the first half, which is more of an introduction to change points and talking about unsupervised change point detection. And then Toby's taking the second half after the coffee break, which will be talking more about supervised change point detection, which is where you've got more of an indication of positives and negatives from that point of view. Okay. So I've got some slides. There's also on the GitHub repository, so this is TD Hock, which is Toby's GitHub page, and it's change-tutorial is the repository. And on there, there's all of the source files and everything for the tutorial, but more importantly, there's also the Markdown knitted documents, which for mine for the first half, when it loads, this is the HTML that you can follow through what I'm talking about. Okay, so when it loads, if everybody's on there already. So that will contain more detail than is on the slides, but basically everything that I say should be in there as well if you want to recap afterwards. So I'll leave that for a second and let you go back to the source one. Okay. So the key for the first half is going to be that you have a copy of the changepoint R package available on CRAN, and also the changepoint.np R package also available on CRAN, and those are the two that we're mainly going to be using in the first half. On Toby's part here, on the rendered section here, that gives you access to a packages.r file here. That will, if you run or source that R file, then that will install all of the packages that you need for the second half. So if you find that you don't have any of them, or your system takes a while to actually install packages, then please do, over the break, make sure you have all of the packages for the second half of the course by sourcing that file, and then that will make the second half run a bit smoother. As I said, for the first half, we only need the changepoint package and the changepoint.np package, both on CRAN. So I'm going to start off talking about generality. So can I just get a show of hands? Who here knows what a change point is? Okay. Who's worked with change point analysis before? A couple? Okay, cool. All right, so I'm basically going to take it from you don't know anything about change points for the people in the room that don't, and then we'll quickly go on. I'm not going to really dwell on the theoretical aspects. If you want to look at that, then there's plenty of papers and references that I can give you to do that. This is a practical tutorial, but I will give you a couple of equations just to get a feel for what is the maths and what we're actually optimizing when we do change point detection. So I'm going to start off with what are change points. I'm going to fix some notation. The same notation is used throughout the course, even in the second half with Toby's. So, at least I hope I've managed to find all of the places where we did differ beforehand. Luckily, in change point detection, we tend to be fairly consistent in how we use notation, so that's not too bad. The main part is going to cover the change point R package, which is mainly around likelihood-based change point detection. And so in that, we will cover changes in mean, changes in variance, and mean and variance, and all of the different options that you have within those functions. I'm going to talk about how many changes and how you decide how many changes there are in a time series. And then I'm going to talk about non-parametric change points as well, which is more on the changepoint.np package. And then if time allows, we'll get to the checking assumptions. If not, there is all of the material already there in the course for you. And throughout the course, we will be talking and doing some practical work. So if you do have your laptops out, I will be giving you some time. There won't be much time because obviously an hour and a half is quite a short for the first half, but there will be some time, and solutions will be posted afterwards if you're interested in terms of what I would do in those situations. There is no right answer, so what you have done might be equally correct. So we're just going to start off with what change points are. If you're from a variety of different fields, you may already know what change points are, but you may know them by a different name. Okay? So in statistics, we call it change points. Thank you. Am I not coming through very well? Thank you. So in statistics, we call it change points, but there's other fields call it different names, such as breakpoints, segmentation problems. Structural breaks tends to be used in economics, regime switching, and also detecting disorder, which you might not necessarily think was change points initially. And they started off in quality control, whereby you were monitoring a process and you wanted to see whether that process was still functioning as you had designed it. And they've rapidly expanded in a variety of other fields. And I'm not sure I've yet seen one where change points hasn't been done, at least in one paper. So the basic setup is that I'm going to call my time series, and I've just realized my first mistake. These should be Zs here, not Ys. This is, there we go. So this is what happens when Toby uses Z and I use Y. We agreed on Z. So I'm going to index my time series Z from 1 to n, and so n is the length. I'm going to talk about time series in general, but in reality, it's any sort of ordered data. So Toby's going to be working later on genomic data, so it's anything that has an ordering to it. So it doesn't necessarily have to be ordered over time. And then the basic essence of what a change point is that at some point, which we're going to call TOR, and TOR is always going to be used for our change points. So at some change point TOR, all of the data prior to TOR and all of the data after TOR are different in some way. And that's the definition of a change, or change point. Okay? And there's many different types of change. So here I've just got 3. I've got my standard mean change here, a variance change in the middle, and then a change in trend on the right-hand side. Okay. And so you can clearly see that the mean is discontinuous in terms of, you've got a mean of 1 for a period, mean of 0 for a period, a mean of 2, and then a mean of a half. And the same thing in the variance, although I tend to put vertical lines rather than putting displaying the means. Okay. And so generally when you do change point analysis, you may have several different questions that you want to ask of the data. Typically the first one is, has a change occurred at all? And if yes, people generally then want to know, well, where has the change occurred? Some people may want to be interested in the difference between the pre and post-change data. So in the mean example, they want to know what the pre-change mean was and what the post-change mean was. And it could even be the type of change in terms of, I know a change has occurred. I don't necessarily need to know what the parameter values are, but I do need to know whether it's a mean change or a variance change, for example. You may also want to know what's the probability that a change point has occurred. So that's sort of getting into sort of the p-value type side of it. And not only what's the probability that a change has occurred, but also, given that a change has occurred at a specific time point, how certain am I that it's at that time point and not one time point earlier or later or something like that. So that's sort of what that is. And more these days, we're wanting to know, well, how many changes has occurred? And when you extend it to that issue, you then have all of the above questions, but for every single change point at that time. One that we don't tend to deal with, or personally I don't tend to deal with, is the question, why has there been a change? So we typically tend to say that there has been a change in the data. Statistically, there is evidence that there is a change, but we don't tend to deal with that next step, which is why has there been a change? So that's typically the point when we hand that back to practitioners and they get to look around it and see if there is some sort of correspondence, correlation with some other thing that's happened at that time point. Okay. So specifically in this tutorial, I'm not going to talk about why has there been a change at all. Okay. So just to get some notation and concepts, if I have multiple changes, I'm going to call them TOR 1, TOR 2, TOR 3, etc. I'm going to deal with TOR 0. TOR 0 here is going to be 0, and TOR k plus 1 is going to be my last data point. Okay, and that's just for notational simplicity. So what that basically boils down to in a change in mean aspect, so how I would write this data set mathematically is that I would say that ZC has some mean, mu1, between time 1 and TOR 1, generalized down for all of the different segments, where a segment is the data between change points. And then I'm going to say TOR k plus 1 is the last mean, and that's the last segment where k plus 1 is going to be n. Okay. So that means that I have k changes in my data. So I'm just going to put up an example of some more complicated types of change here, and we're going to kick off the interactive nature by saying, is there anybody in the audience here who could tell me whether there's a change, what the change is in terms of what type of change, and where it is in either of these data sets? Yep. On that one? Or this one? Yep, okay, so on the one on the far right, and where is that change? It's not. We can talk about gradual changes in a different tutorial. But anybody else for any others? So we've got a change in sinusoidal behavior on the right. The guy said a change in periodicity. It's a change in correlation on the left. Anybody for any other type of change or where those changes might be? Yeah?
There are changes in mean in the first part of the left graphics when it goes up and down.
Yeah, so there are some changes in mean. That's actually induced by the correlation that's there. So there's not actually a physical change in mean. That's just high correlation on that side. But yeah, it's a good spot. Okay. So hopefully we can all agree that it's much more difficult than this situation here. Okay. This situation here, you might say, okay, maybe I don't need change point algorithms to detect this. But in this situation, you do. Okay. So there's both a change in correlation just on the left. Okay. There's more than one change. And you're going from positive correlation at the beginning to negative correlation at the end in 3 stages. And then on the right-hand side, we just spotted the change in sinusoid, but what you may have failed to notice is there's also a change in variance. So you can see sort of the variability here at the beginning. It's easier to see in the peaks and the troughs. It's fairly small, whereas on this side, it's actually fairly large. Okay. So it's a bit more difficult to see when that change occurs because of that corruption with the sinusoidal noise. But hopefully you'll see that it's not all easy changing means that we're going to be doing in the tutorial. So there's 2 distinctions that I just want to make very clear before we start getting into stuff, and that's the difference between online change point detection and offline change point detection. So in online change point detection, this was really the motivation for the field existing in the first place. And basically, you can think of that like the process control example. So you make something new, you get data on what that is. You then want to say, well, based on that data, has my process gone out of control or not? Okay. And the goal there is that you want to manufacture a small number of items that are faulty before you detect that they're faulty. Okay. And so that's really the quickest detection. You can also think of it as computer networks. You want to detect as quickly as possible if you've had an intrusion in the computer network, but you're actually getting data all the time. So in offline change point detection, in contrast, you have all the data at the start. You're not expecting any more data to arrive. So you can obviously see there's a sort of overlap between the batch data and the offline data, in the sense that if you have batch data, but you can process all of the data in almost like in an offline setting before any new data arrives, then that's just the same as an offline setting. Okay? Where you're wanting to do batch data, where you receive a batch of data and you have to process it really, really quickly before you get the new set, you're then wanting to update what you already know from previously rather than reanalyze the whole set of data again. Okay. So the goal in offline change point detection isn't about quickest detection or anything like that, because you've got all the data in one go. It's purely about accuracy. Okay. So in online change point detection, they don't really, they want accuracy of where the change point is, but they will forgive a bit of inaccuracy at the expense of well, if they can detect it quicker, they're happy to accept some inaccuracy in where the change is. Okay. Whereas in offline, the goal is just getting the location correct. Okay. And so this is often used in genomics and audiology and lots of other places where really it matters that you get that change point correct. Okay. So just pictorially, this is what it means. So I'm getting some data here. So I have the data up to the red line in online change point detection, and I detect the change at the black line. And the difference between the black and the red is my detection delay. So that's what I want to minimize. But I don't have the data in gray yet. Okay. Whereas in offline change point detection, I have the whole lot. And I detect the change point at the black line with all of the data. So, as I said, we're going to use two packages today, the changepoint package and the changepoint.np package. There are many other changepoint packages out there. I've listed a couple here because these are quite well known for different types of changepoint detection. So if you want to do regression, that's not covered in the changepoint package and it won't be in this tutorial. There's a struct change package by Achim Zeilis for that. BCP if you want to do Bayesian changepoint detection. CPM if you want to be online. Although I do have a package changepoint.online that will be out soon. And I often get people asking me questions after a tutorial like this or using the changepoint package about dependencies. Okay, so if you have correlation in your data, so the MCPT package will test between a variety of different mean, trend, and or A01 structured data. So it'll basically fit all of them and tell you which one's the best model. So that currently doesn't work for really long data sets. As you can imagine, it's lots of models that you're fitting. But the back-end code is being put into C as I speak by one of my interns, so hopefully that will be much quicker by the end of the summer. So going back to what this tutorial is all about. So I'm going to start off with single change point detection. I'm going to generalize in a few minutes. So I'm going to have ZT is my data again. I'm going to have theta t is my mean. And so you can sort of see that the theta t is the mean at every single time point. And then these, I'm going to impose a condition on these that they're piecewise constant. And that retrieves this piecewise constant mean structure here. Okay. So if I'm thinking about a single change point, I'm basically comparing the pre-change data with the post-change data. Okay. And so one way that you can do that is you can do a likelihood ratio test. You're essentially doing a test between a model that has no change point and a model that has one change point. Okay. And to do that, what you basically do is oh God. You basically are splitting the data at the change point because we're going to assume that the pre and post change data are independent. And so you literally take the likelihood of the first half, the likelihood of the second half, and add them together. Okay? And that literally just gives you the likelihood of the whole data set, and you can just add them up across the different segments. Okay? And then, I really should bring my mouse. What you then do when you've got the likelihood of the data with the change point is you then compare that to the likelihood of the data without the change point. And that's just the likelihood of the entire data. Okay? And that's just a simple comparison where you're comparing one model with the other. The difference is that because the change point is a discrete variable, we can't maximize this over, by differentiating and then setting the differential to 0 to maximize our TOR. Instead, we have to take each individual value of TOR and evaluate it at each one and then decide which one's the best. Okay? And that may seem very simplistic, but that's exactly what we do. Okay? And then the way you decide whether you have the change point model or the no change model is that you look at this likelihood ratio here and you say, is that larger than some threshold value? And so this threshold value notionally, you think, well, within a no change data set, what do I expect the noise level to be? And therefore this lambda here can be related to the noise level, and you can have a confidence interval value for this lambda as well, in the sense that, if you want to be 95% confident of a change, then you can set this lambda so that you're 95% confident. Okay. And so if we decide there is a change point, then the change point is literally just which value of TOR maximize this likelihood ratio. Okay. And so that's the essence of change point analysis, is you're basically just comparing the model that has no change point to the model with the change point in and deciding which one's better. Okay. So how do we do this in the change point R package? So essentially, I split it up into types of change. So you can have a change in mean, a change in variance, or a change in both the mean and the variance of your data. These are really the only three functions that you should need. There are obviously other functions there for interacting with the output of these, either in terms of the class function. So all of these functions here, output an S4 class object, are called CPT. So there are other functions to extract the data and things of that, and to plot and etc. There's 5 data sets in the package, and there's also other R functions if any of you want to extend the package in terms of new cost functions. I'll talk about what a cost function is in a minute, or if you want to add new ways of finding change points, everything's there ready if you want to do that. So I'll spend a few minutes talking about the S4 class, because that's what we're actually going to use in the tutorials. So once you've done the analysis, everything that was used in the analysis is contained in that class. So that includes the data set that you were analysing, what change points were found, if any, what parameter estimates there are, what penalty value you set, how many change points, maximum number of change points could you actually find in that data. All of these things are stored together, along with the date and time that the change point analysis was run, to try and aid some reproducibility for that. Okay. It's an S4 class, so typically you would access the slots using the @ symbol, but I find that a bit ugly and not helpful for new users. So I've actually implemented the essentially generics to access each of the class slots. Okay. So if you want to access the data set, then you do data.set of the object, and then that, and same here for the change points of the CPT object, and it will give you that slot name out, okay, just to make it a bit more user-friendly. You can use the plot and the summary, as we will do in the rest of the tutorial. And there's also some other generics, such as NCPTS, which is the number of change points, and if you use that, that will give you the number of change points, rather than you calculating it from the output of the change points. Same with seg.len, it just looks at the difference between the change point values. Okay. And so we'll move on to the first one. Once I've finished talking about cpt.mean, I'll give you a task to do. So the structure of the function is like this. We import our data. We have a penalty function, so this is basically that lambda that I was just talking about. The default is MBIC, which penalizes against very short and very long segments. So it sort of tries to balance out between the two. We have pen.value, which has a default of 0. So this doesn't really come into play unless you're changing the penalty value. So pen.value, if you're wanting an asymptotic lambda value, then you can set the type 1 error with this pen.value. Or if you're setting penalty to manual, that basically means that you can input anything that's either a number or a character that can be evaluated to a number within the pen.value option here. So the default method is amok, which is at most one change. And then there's some other methods which I'll talk about later in the tutorial, but we're just going to stick with a single change point for now. And the test statistic here, we've got normal or QSUM, which is a non-parametric test statistic. They're actually exactly the same, just one has a normal assumption and one doesn't. But actually, it boils down to being exactly the same. Class is set to true. If you don't want a CPT S4 object out of it, then you can set that to false, and it will just return the change points to you. Again, if you think that calculating the parameter estimates might take a long time, then you can set that to false and choose to calculate them later if you want to. And the minimum segment length is sort of the next important option. It's set to 1, which is the default, in the sense that you have to have at least one data point between your changes, and therefore you can control this value here. You can say set it to 10 if you don't believe that any change point segments of length less than 10 are actually meaningful. Okay, so I know some people in the oceanography who basically, if you have a changes close together less than 10 years, then they say, oh, I really don't believe that. Ecological stuff can't change on that smaller time scale. So they would often set the minimum segment length to 10. Okay. And this is just a very short example here. So we can set our C just for reproducibility. We then generate some data here. So I've got 100 data points with mean 0 and variance 1. And then we change and have a mean of 5. Okay. I'm going to just use the default values. So if you remember, the default values here is a normal test statistic, MBIC penalty, and at most 1 change. Okay. So if I do that, and then I'm going to use CPTS here, and this just gives me the change points from this analysis, and that gives a change at 100, and we'll go few because we simulated it with a change at 100, and you get a change at 100. Okay. And you can do exactly the same thing, but with the QSUM test statistic. Now, because I'm just sort of going to show you some options here, you can set the penalty to manual, and then the pen dot value is 1. Okay, so that basically sets that lambda value to be 1. So if you don't have a difference in likelihood ratio of more than 1, then you're not going to find the change. Okay. There's a warning here in the sense that the traditional penalty values are not appropriate. So using MBIC or using asymptotic penalty values, that they have no basis in the QSUM world because they're not theoretically proven to be optimal in any sense. Okay. So it's just a warning there for people, just in case they are blindly using the defaults or other things, just to flag it to anybody. And so we can then use the plot function, and I'm literally doing plot on that output here. So I'm just taking the output of my analysis. I'm just doing plot, and it'll automatically plot the original data for you as a TS object, as you can see here, and it'll overlay the mean values. Okay. As we'll see later, if you've got a change in variance or another type of change, then it automatically knows what the type of change is and does it automatically for you. Okay. So that's sort of a basic example. I'm going to give you a few minutes now to try it out yourself. So there's some data here that's available inside useR from the River Nile. And essentially the question is there a change in this data? So there's a hypothesis that there was a change due to the Aswad Dam. But I'm going to give you a few minutes to see if you can determine if there is one. Hint, hint, single change point in mean value. That one? I'll show you in a minute. Okay, so hopefully you've had enough time to just type that code in. If not, I'll encourage you to do it later. So just to show you the how I would have done this. So if I'm using the default values, I'd just do cpt.mean on Nile. I then do cpts to get the change points out, but you'll notice that gives a time point of 28 when the original data is in years. Okay, so when you're putting in a time series object into cpt.mean, it does retain all of the time series information, and so you can do cpts.ts, which is the time series. So cpts gives almost like the index, and then cpts.ts gives you the time series value, which is 1898. Okay. Equally, if you wanted to get the parameter estimates, then you can just do param.est, and that will give you, it automatically gives you a list, and $mean there gives you the pre-change and post-change mean here. So you can see that it's decreased from around 1,097 to 850. Okay, so that's basically, oh, I've even got a plot here. If I do plot of it, then it automatically plots. Again, it automatically plots with the time series information. So this is what we determine is the statistically appropriate single change point in this data. Okay. Did everybody manage to generally get that? Nods of heads? Yep.
I tried to run the model with cpt.mean var. So I got the same result, but I don't know if it's exactly, it doesn't show whether the change is in mean or variance.
That's true. I'll talk about that in a bit. So there's a gentleman here that's used cpt.mean var instead of cpt.mean, and found that the change is at the same place. Was that right? Yep. But it's not clear whether the change is in the mean or the variance. So we can discuss that when we get to cpt.mean var later. Okay, thanks. Okay. Anybody else before I move on?
Can you go back one slide, please?
Yep. Is that all right? Cool. So I'm now going to move on to, oh, yep, sorry, before we go. So the question is, can I clarify what cpts.ts does? So basically, the Nile data here, when you input it, is a TS object. So it's stored as a time series object inside R. And so what cpts does just gives you the index of where the change point was found. So it's time point 28. And then cpts.ts basically says, well, time point 28, what is that value in the TS object? And that is 1898. Yeah, so the param.est is the parameter estimates. So that's going to give us the parameter estimates that we've got. So because we've done a change in mean, it gives us the pre-change mean and the post-change mean. So when we come later to do multiple change points, this then becomes potentially a very long vector. Okay. Any more before I move on? We're good? Okay. So I'm going to talk about multiple change points now. So any of you who are working with real-world data will probably see that it's very rare that you find a time series that definitely has at most one change point. And normally we're actually looking at potentially multiple change points. And crucially, this can still find a single change point if there is only one change point in the data, but it can find more changes as well. So my tor now here is going to be a vector. So as I said earlier, tor 0 is 0, tor k plus 1 is the end of the data. And this formulation is just so that when I write this sum here, it makes sense. Okay. And so if we think of the likelihood ratio test, which was basically comparing, adding up all of the pre-change and post-change likelihood, and then comparing it to the null likelihood, what we're actually doing is this formulation here. So this is adding up the negative log likelihoods here. So I'm now trying to minimize this rather than maximizing my log likelihood. So I'm adding up all of my likelihoods across all of my segments here. So because my k here, the number of change points is either 0 or 1, this is basically either the likelihood of the whole data or the likelihood of the pre-change plus the post-change. Okay? And then I've got lambda k here, which is k is either going to be 0 or 1, so I'm either adding nothing or I'm adding my lambda. Okay? And if I'm looking at the minimum of that over all possible change point values Tor, that basically just recovers the same thing as what I was doing previously. Okay. Previously, I had I was directly comparing the no change and the one change by taking the difference between those two and saying, is that difference larger than lambda? Now, I'm basically adding that lambda to the change point model, the one that has the change, and basically comparing that, well, is that bigger or smaller than my no change likelihood? Okay, so it's exactly the same premise, just a different notational form. Okay. But hopefully you can see that when you put it in this context, you can easily generalize this to multiple change points. Whereas if you're trying to generalize the likelihood ratio to multiple change points, you're sort of thinking, okay, well, I've got my single change option where I'm adding up two things, and then I've got my no change option. When I add another change point, what am I comparing? Am I comparing two change points to 1, 2 to 0, 1 to 0? What am I doing? Okay. Whereas here, we're basically calculating the penalized likelihood of every single model option here. So generalizing this, I'm literally just removing this restriction on the k, so everything else is exactly the same. I'm just saying now, instead of k only being no change points or one change point, it can now be any number of change points. Okay. And so, as I said, this can be viewed as a special case of what's called penalized likelihood, and that's basically just likelihood, but with a generic penalization factor here. So now so the difference between here and the next side is that here I'm counting the number of change points, and that's how many lambdas I have. Here, I also have lambda times something that depends on the number of change points, but it doesn't just have to be k. It can be some function of k. Okay. And so this is a more generic version of the previous, and this is just penalized likelihood for anybody who knows what this is. But the key thing here is that we have to obviously choose this function k, we have to choose the lambda, and we have to find a way of optimizing this so that we actually retrieve the minimum of this function over all possible k and all possible Tor. Okay. And so rather than writing this as likelihood here, we can actually make it even more generic, and we can just write this as a cost. Okay. So you may have likelihoods, you may have some non-parametric cost, whatever you can come up with, provided that you can basically take the cost of a single segment and add them up over all segments to get the cost overall, you can use this framework. Okay, so we're now sort of moving beyond likelihood. Okay. But there's a huge open research question, which is actually, what penalty should I use? Okay, so what should this, and I've gone to beta, apologies. There should be lambda fk here. So what should my lambda fk here actually be? Okay. Should it just be k? What should the lambda be? And that is an open research question even to this day. Several very clever people have tried to attempt to answer it, but in reality, ultimately it depends on some assumptions, and the way that you can check those assumptions in real data is not clear in any sense of the word. And as soon as you move away from those assumptions, it's no longer optimal, and therefore, why choose that over something else? Okay. So there's many different penalties. Ultimately, it's down to user preference as to which one you choose. Yep.
The algorithm is sensitive to scaling difference? How does scaling?
Yeah, so basically, when you're working with the likelihood, as long as you're working with the likelihood, then it doesn't really matter about scaling your data. Okay. When you're working with other cost function forms, then obviously scaling your data does matter. And that's one of the reasons why the Q-sum, you can't use traditional penalty values, because it's a scaling factor. I should say one caveat to that is the cpt.mean function that we've just been using. You'll have noticed that in the parameter estimates, it didn't give a value for the variance. And the reason for that is that it assumes the variance is 1, because ultimately you're having to estimate the variance across the entire data, and you can't estimate the variance without knowing what the means are, so you then become into an iterative loop. So you can't, because the parameter value for the variance is across the entire data, you can't actually solve the problem. So you have to make the assumption that that is equal to 1. So if you're using the cpt.mean, you should be scaling your data. Okay. So the challenge in this is that what actually are the values of my change points? And I've got an M here, and that should be a K. Apologies. What is K, the number of change points? Just to give you an idea of the scale of this problem, if K is known, so that means you know the number of change points, then there's a huge amount of solutions. So if N is 1,000 and K is 10, then we have 2.634 times 10 to the 21 solutions. To solve the problem exactly, we have to check every single one of those and see if it's the best. Okay. So the main thing in the title of this is optimal change point detection algorithms, and so it's about how we can actually use different methods to solve that solution exactly, preferably, and very, very fast. Okay. So the methods that are available in the change point package, we've already seen the at most one change. If you want an approximate solution to that problem, but computationally fast, then you can use the binary segmentation, which is the binseg option. The earliest is in Scott and Knott in 1974, and this is order n log n in CPU time. If you don't mind being a bit slower because you want an exact solution, then you can use the segment neighborhood, which I know Toby's going to talk a bit more about later. That's a SegNA option, and that's Ager and Lawrence in 1989, and that is order qn squared, where q is the maximum number of change points that you want to search for. In contrast, if you want both properties, you want to be fast and exact, then you can use the pruned exact linear time, which is the PELT option, which is an algorithm that I helped to develop. And at worst, that is order n squared, and you're assuming a linear penalty function here. And if as you go through your data, you see more and more changes, then that will be order n computational time. And whilst order n seems better than order n log n, in reality, the coefficient of this is larger than log n. So typically, even though this looks faster at order n, it's often comparable or slightly slower than binary segmentation. But we can have a look at CPU times later on. I'll do a quick plug for one of Toby's algorithms, which is FPOP, which is a reference at the end of the tutorial. And that actually can be faster than binary segmentation, which was a great hurrah in the fact that you can get an exact method better than the faster than the approximate. So that was quite nice. I'm going to move on to the second one now, cpt.var. I'm going to quickly whiz through both cpt.var and cpt.meanvar, and then we'll have another chance to practice on those. You'll be glad to know they've basically got exactly the same structure as cpt.mean. So the majority of arguments are the same. As you can sort of see from what's coming on. No.mean is a true-false argument here, and that's basically, do you know what the mean is? So if you're doing some form of designed experiment, you may know what the mean should be, and basically you can remove a degree of freedom if you do that. So if you put no.mean is true, and you give us the mean there, then basically when you're calculating some automatic penalties, it doesn't count that as an estimated parameter. So ultimately, it marginally affects things sometimes. As you can imagine, if you're really that close anyway, then you may or may not believe. And again, the test statistic here, it can be a normal distribution, or we can use CSS, which is cumulative sum of the squares, and that's a non-parametric version. They are not the same. And for a variance, the minimum segment length default is 2 because we're assuming that we have to estimate a mean in this data, but obviously you can increase that if you want to. So just a quick example again. So again, I've got setting my C just to make it reproducible. I'm going to have a variance of 1 to a standard deviation of 2, standard deviation of 10, and then down to 9 again. Okay. So going from standard deviation of 10 to 9, as you'll see in a minute on the next slide, it's actually really small. So in terms of whether you'll be able to detect that or not, there's a question on that. So we then just use cpt.var. So we've got cpt.var instead of cpt.mean. And I'm going to use the PELT methodology here. I'm going to set a manual penalty at 2 log n. This is exactly equal to the SIC penalty. So if you wanted to substitute that in, you'll see it's exactly the same that what you get out. This is just to demonstrate the fact that you can put formulas in the penalty value if you want. So you can use n, it knows what n is. There are several other options of what the algorithm knows as variables. So you can have a look in the help file if you want to see more of that. Again, I'm going to do cpt.s to get my change points out, and I'm doing param.s to get my parameter estimates. So it's exactly the same as what we were doing before with cpt.mean. My change points are 102 and 200. So you'll notice that I'm 2 time points out here, and I'm bang on with the second one, but the third one, so there should be a change at 300, that's not detected at all. Okay, and we'll see on the next slide whether by eye you would be able to detect it. Okay, and so I'm estimating the variances here. So at 0.8, I'm fairly close to 1 there. This one here is fairly close to 4, and this one should be 100. Well, it should be sort of between 100 and 81, because I've merged these two segments, and sort of we've got about 92. So that seems okay. And it's estimated a mean because I didn't give it one, so it's also returning the global mean here. Okay, and the mean can be estimated independently of the variance, and so therefore, because so that's why that's returned. So if I'm looking at the data, you may say, okay, I can sort of see a change in mean, change in variance here. There's a clear change in variance at time point 200 here, and I can argue that I've got some more extreme values here than I do on this side of 300, but I'd be very hard pressed to put where that change was. Okay, and so if you think about it distributionally, if you take two normal distributions, both with mean 0, and one has a variance of 10 and one has a variance of 9, you'll understand why this is a very difficult problem, because there's so much overlap in the distribution, and we've only got 100 time points here to assess whether that's a distributional difference or not. Okay. Yep.
Will it make a difference if you only examine the last 100 points?
No. In essence, what the Pelt algorithm is doing is precisely that. So what we do is we go from the beginning of the data to the end, and we're constantly saying, where is the last change point? And so it doesn't matter whether you chop it at 200 and only look at the last 200, you get exactly the same answer. Some other people also said, well, what if you run the method backwards? So you start at 400 and you go that way, and it works exactly the same. So yeah, yep.
Would it get better if you would have more points of each?
Yep, it would. In general, as a general rule of thumb, and this is a rule of thumb, in length 100 data, you need a variance change of 3. So in the sense of the ratio between the pre and post change variance needs to be 3. So that's actually quite huge. If you're talking down here where you're going from 1 to 4, that doesn't seem very big, but when you're saying actually if I've got a variance of 100, I need to go to a variance of 300 to be able to see it with 80% power, that's huge. Okay, so there's things like that. I'm demonstrating here, sorry, this is why I have ratios of true variances here, because really you want something, if one of these is, if they're all above 3, then I believe it. Okay. So here I'm demonstrating that you can use cpt.width. It's an extra plot parameter here, and that basically changes the width of the lines. So if you look at the previous plot, they were thinner lines. There's other options that I'll also demonstrate later. So moving on briefly, I'll give you a chance to use cpt.var in a few minutes. The last one is cpt.meanvar, and here again it has exactly the same type of structure as cpt.mean. Now you've got a bit more choices in your test statistics, so you can have normal, gamma, exponential, or Poisson distributed data. The shape parameter here, when you're looking at the gamma distribution, you've obviously got shape and scale. We assume it's the scale that's changing, and the shape is fixed. So this is the assumed shape parameter, a bit like I said in cpt.var, you've got the no.mean. It's exactly the same premise coming through there. So if you know the shape parameter, or you put an estimate of the shape parameter in there, then that will be used by the data. And again, the minimum segment length is 2, because we're estimating a mean and a variance per segment. So again, I've got another example here. Here I'm generating from an exponential distribution with, I've got segment lengths of 50 here and different rate parameters coming through. Again, I just do cpt.meanvar, I have to remember to change the test statistic because the default is a normal distribution here, so I'm changing this to exponential. And I'm just to give you a feel for a different one, I'm going to use the binary segmentation. So if you remember, this is approximate. So what it basically does is it finds the largest change point in the data as a single change point problem, cuts the data at that time point, and then searches for more data, more changes either side of that change point. And so when you place one change point incorrectly, then that will affect all of the positions of the future change points, and that's why it's an approximate algorithm. Because I'm using binary segmentation here, I have to do Q, and this is my maximum number of change points I want to search for. Computationally, you want this to be small. Practically speaking, you want it to be larger than the true number of change points that you have in the data. Okay, it's pretty fast because it's written in C, so you could set that to 100 or 1,000, depending on the length of your data, and it would be absolutely fine. If you do set this larger than your data size or larger than the maximum number of allowed changes, given that they have to have segment lengths of at least 2, it will warn you about that. And then I've changed my penalty to be the SIC here. So again, I'm just using CPTS to get my change points, and I retrieve 50, 100, and 150 as was simulated. And I'm using param.est, and it knows that it's an exponential, so it returns the rate. Okay, so it automatically can deal with that within the same type of code. And again, cpt.width, I've changed it to 3, just so it's clear. But you've also got cpt.col, which is the color of those lines, and I've changed them to blue this time. Okay. It basically accepts any color palette that you've got loaded. So I'm now going to give 2 examples. So one's the FTSE 100, so the data's available within the change point package. So once you've got the change point package loaded, just do FTSE 100, and it's data from 1984 until 2012. So it covers the financial crash here, which we can argue over whether is a cause for a change point. And there's also, so for that data, I want you to see if there's any evidence for multiple changes in that data. So you can obviously sort of see we've got the crash here as well in the late 80s. And then there's also some other data. So this is a bit longer. This is human chromosome data. So it's 3 kilobyte windows from 10 meg to 33 meg long. So this is an example that isn't time series data, it's just ordered data. And again, here I want you to use the mean var. So if you actually zoom in to this data, you'll see that there's actually changes in mean and variance in this data. So so use the mean var function to identify the regions within those. Okay. So I'm going to give you a few minutes to do one or both of those. If you can do both, I'll be very impressed. But yeah, have a go at those. manual is still beavering away, but we're quite tight on time, so I was going to...
I was wondering for the incremental data, it's involved in the proportion, like the binomial distribution. Do you have any implementation for the binomial model?
Not currently in. I think it's, yeah, if you want to do that, then you use GM stuff, the negative binomial. Okay. So I'm not going to go through the FTSE one, mainly because I want to use the HG1 one for motivation for my next slides. So if you use the default penalty, then you'll get a hell of a lot of changes. I don't know if anybody managed to get through to that one. In consultation with some biologists, we decided that the most appropriate penalty was going to be a penalty value of 14. So it's actually quite a lot larger than the default penalty value. And even with that, if we do NCPTS, so this is the number of change points, on our CPT object, we get 805. Okay. Similarly, if you do summary, it will also return that you have 805 changes as part of the summary. Okay. So I don't advise you doing CPTS because you just get a long 805 long vector out, which is not very meaningful. If you do the plot, then because it's a mean variance object, you get all of these little dots coming across. And so this is sort of all of the changes that you see with that. Again, I'm showing here that you can actually do use standard plotting functions to change the labels of the graphs if you want to. So part of this sort of brings me to the next part, which is how do you actually decide the number of changes? If you use a default penalty value and you actually look at it and go, I don't believe that at all, how do you actually, justify choosing another option? Okay. And so when you look at this, you say, well, does that appear, is that reasonable? I've spoken to some biologists and they say it is, but looking at it personally, there's a lot of data there, so if I looked at one specific chunk and I zoomed in, I might say, yeah, that looks reasonable. But if I look at the whole lot like this, I look and you go, whoa, what's going on? What are these bits up here? Are these just outliers? Are they really changes? How long are they? Okay. So that sort of brought us to a new piece of work, which is called CROPS. And this is essentially short for change points for a range of penalties. Okay. And so when you're using the PELT method, you can use the CROPS penalty, and you basically supply it with a minimum and a maximum penalty value, and it will find all of the change points, segmentations in between those two values. Okay? And the important thing is that when you're traditionally looking at this and going, oh, that's too many, let me increase my penalty a little bit, and then I'll get a few changes. And then you increase it a bit, and then you go, oh, actually, no, I don't quite believe that. I think there should definitely be a change here, so let's decrease it a bit more. And when you're doing that, you end up expending quite a lot of time in trying to fiddle about, especially because a very small change in the penalty value can either be a very large change in the number of change points or no change in the number of change points, depending on where you are on the penalty spectrum. Okay? And you may be searching forever for, I want 5 change points in my data. I just want to find my penalty value that gives me 5 change points. And it may not exist. Okay? There may be no penalty value for which 5 change points is optimal. Okay? So this sort of brings in the CROPS. And essentially what it does is it does an efficient version of that manual search. And so it knows that when you put in a penalty value of 5 and a penalty value of 500 in this example here, it knows how many change points are at 5, how many are at 500, and therefore where a crossover point is likely to be. Okay? And so when you first start this algorithm off, it will tell you the maximum number of runs that it has to do. So this is the maximum number of times it has to run the PELT algorithm. Okay? So if you've got shed loads of data, then it may be that this number here is too large, and you think, I don't have enough computational time to wait that long, in which case you can change the values of your penalty here and then rerun it until this value is a bit more realistic for you, and then you can just search smaller ranges instead of a huge range. Okay, but the maximum number for this range, which is quite large, is just 10. Okay, what that means is that when I have 5, a penalty value of 5, I still have relatively few changes. Okay, and this is because this is short data that doesn't actually have many true changes in it. And then it will show you progress as you go through and how many runs it's completed. And so out of a maximum possible of 10, it's only had to do 9. Okay, so it will tell you how many it actually does as well. So this is sort of an estimate, an upper estimate of what you might need to run. And so the great thing with that is that I then have all of the segmentations with penalty values between 5 and 500, which includes all of those default options that I had. Okay, and so I can use cpts.full, and so previously we were just using cpts. Now I put the .full after it to get the full segmentation. So there's a penalty value between 5 and 500 that gives me no changes, which is this bottom value here. And then as I decrease my penalty value, I go up here. So this is basically a penalty value of 5 at the top, 500 at the bottom, and these are my changes in between. And you'll notice that there's no segmentation for which there are 6 change points. Okay? You either have 5 or you have 7. You can't have 6. Okay? And part of that is because you need to introduce this 375 and 379, which is a fairly short segment, both together. So that's when we look at the data on the next slide, you'll see that's quite a short segment where the mean, where the variance is just actually very small in this example. But in other examples, it could be due to outliers, especially when you've got mean. If you're looking for a mean change, then outliers often come as 2 change points together. Okay. You'll also see that the PELT algorithm is, as you add change points, you can actually change the positions of previous change points. So here we've got 102 and 102, but when we move to 4 change points here, the 206 and 201 stay the same, but when we add the next one in, we need to shift the change point. Okay. And this is because we're using PELT, which gives us an exact search, whereas if we were using binary segmentation, then you wouldn't have that. You wouldn't have that movement coming through. Okay. And you may be thinking, okay, well, what penalty value gives me each of these segmentations? And so again, you could have used pen.value previously, and so the more generic version of that is pen.value.full. And this basically gives us 5 at the smaller one. It doesn't give us 500 at the top because it's actually 474 where I go to no changes. Okay, so between 474 and 500 I have no changes. Well, 474 and infinity I have no changes. But between 5 and 5.4 I'll then have the top line, which is 8 changes, etc. as you go along. I haven't actually printed them all there. And so you may then say, okay, well, I quite like the look of this 5 change example here. I want to see what that looks like graphically. So therefore, I can do plot. And previously, we were just doing plot of the CPT object. Now we can use this extra parameter, which is number of change points is 5. Okay. And I say I want 5 change points, and therefore, it plots me the 5 change points here. So if you go, so you've got 1, 2, 3, 4, 5. And you'll see that this is quite a small one here. A small segment there, with quite a large variance, which you may or may not believe. So if you remember, the actual truth for this data set was 3. There was a change at 100, a change at 200, and a change at 300, and this was going from a variance of 100 to a variance of 821. And so that one there, we said we couldn't see. And actually, when you add more changes, you don't add a change at 300, you add it more in this section here. Okay? Maybe interesting. If you maybe have too many changes to look at, or you just want to see and actually kind of a diagnostic as to what number I should choose, you can do plot, and instead of having the number of change points there, you can put diagnostic as true. Okay, and what this plots is the number of change points along the bottom and your test statistic across the top, or rather the difference in test statistic. So you can see here that you've got a huge decrease going from 0 change points to 1, a smaller one going from 1 to 2, and then from 2 onwards, it's really tiny. Okay, and the premise behind looking at this is a bit like a scree plot in principal component analysis, where you're wanting to choose the number of components. When you add in true change points, you're really better fitting your data. And so when you're better fitting your data, your difference in your test statistic is huge. Okay, When you're just adding change points that are due to noise in your data, the difference in test statistic is really small because they're not really there, and therefore you're getting a very small difference here along the bottom. So ultimately, this is what we call looking for the elbow in this plot, and so therefore you can say 2 changes is what I should have in this data. Okay. The key thing when you're doing these plots is that you want to be getting the 0 if you want to be able to say, is there 0 change points? Because if there's 0 change points, this will be rather flat anyway. Okay. When you're looking at larger numbers of change points, maybe you want to say, well, is it 800 or 850 changes like in the HC1 data? There's no necessity to go down to 0, but sometimes going down to 0 can give you that scale of actually, well, between 800 and 801, I have quite what looks like a relatively large change, but actually if I take it back to 0, that change is going to be futile. Okay. Yep. Can you shout?
Across all tests there, does the occurrence of the particular change point have any meaning in terms of stability of that change? If now you take 2, say, for your best option.
Yep, okay. So
Back to the plot there, I mean, you see a lot
that one?
of reoccurring breakpoints there. Does that have any meaning for the stability of that particular point?
Yep, so what you could... Yeah, so what you can look at is you can look at the width of these intervals here, in the sense that so for the single change point, it's stable between 54 and 474. So that's a long interval where you only have 1 change point. And then between 54 and 6, that's where you're adding the second change point. And so that's a very long interval where you've got the second change point in. So you can look at stability like that, but if you have quite a lot of true changes in your data, you'll have probably quite short segments between them. So when you're getting along to sort of the region of like 800 change points, then looking at stability of segments doesn't necessarily make as much sense. But yeah, that's another way that you can look at it. So you can plot, instead of plotting number of change points here on the bottom, you can plot the penalty value that gives that number of change points if you're interested more in stability. Okay. So I'll give you an example, a task on that in a few minutes, but I just wanted to move on to changepoint.np. So we're now moving from the changepoint package to the changepoint.np package. So notionally, this is for non-parametric test statistics. You'll notice that I've already mentioned 2 non-parametrics that were already in the changepoint package, the QSUM and the QSUM of squareds. Those will be moving over to the changepoint.np package when I get time to do it. But they were originally in the changepoint package, and then a new non-parametric work has been going on at Lancaster, and so therefore we felt a separate package was warranted rather than making changepoint too big. So we've got cp2.np now. Again, it has the same structure and the same feel. It still has an S4 class structure with CPT class. The main difference is just it does non-parametric stuff. Okay. So here, currently, there's only the test statistic of empirical distribution. If you look on the GitHub page, you'll see that there's actually a few more coming. Don't try and use the code yet because it doesn't work. But in terms of the fact that it gives you change points, but they may not necessarily be the right answer at the moment. So you'll see they are in development though, and they will be released to CRAN once it's all done and working. Again, you've got the minimum segment length here and all of the other options that you've got coming through. And then for the empirical distribution test statistic, we have n quantiles. So this is looking purely at a change in distribution and using the empirical distribution function, so the ECDF, if people are familiar with that. And when you do that, you want to look for a change in distribution. So we're not constricting to mean or variance. You're saying, is this distribution the same as this distribution? Okay. And to do that, we need to look at a specific number of quantiles to have a look at that. So the default is 10 quantiles here. It doesn't evenly distribute them across the whole space. If you have a look in the paper, there's reasoning why you should have a non-asymmetric or non-equidistant spacing for those quantiles, but it automatically chooses where they are for you. Okay. So that's the cp2.np function. Just as an example, so there's some code here that will generate a non-parametric change in distribution. I still have some normal errors on there, but ultimately the mean is definitely coming from a different distribution. And if I look at this, I'm going to do n's 1,000, so here I should be getting changes at 100, 130, 150, etc. And this is what we're getting out here. So again, I'm just using cpt.np. I have to do method is pelt for this. I could do crops or not do crops, depending on what you want. The option's there. And Kaylee, who created the package, tends to use 4 log length data as the number of quantiles coming through. It's not the default because she felt like, you know, up to a minimum of 10, so really you probably should have a maximum on 10 and this number. But this comes through. If you actually change the n quantiles here, you actually have to take it down to 1 quantile to get the wrong answer. So it's not, you know, it's, for this example, it's very stable with the number of quantiles, but I would recommend, if you're using this, to have a look at a few different quantiles, number of quantiles, and just see if it does change the results, and therefore you may want to think carefully about the changes that do change. So this is just a plot of that output. Again, because we're not estimating the mean, we're just estimating a change in distribution. It doesn't put a mean value on. This is a clear change in mean as well as a distributional change. It just puts the vertical lines where the changes are. And as you can see, they're sort of coming in the right place. Although, again, they're fairly obvious in this example. So I've got 2 tasks here, one for crops and one for CPT-MP. So for crops, I'm saying look at the FTSE 100 data or the HC1 and use the crops technique to determine an appropriate number of changes. And then for CPT.MP, inside the CPT.changepoint.mp package is some heart rate data. It's actually Kaylee's heart rate data. She went for a run and she decided to upload the data to the package, so you can have a look at that and see if there's any change in heart rate. Interestingly, she's also put elevation and things on there, so you can see how the changes in heart rate actually correlate with changes in elevation and things as well. So I'm going to give you a few minutes to have a look at that before we move on to looking at diagnostics. Okay. So I will put up, I think it's probably more important to put up the crops one because it's different from just the changepoint.np. So I'll put that one up for you to look at. So I'm conscious everybody's going to want coffee in about 10 minutes, so I will continue on. If you've not had time, then don't worry, both me and Toby are quite welcome to have any comments whatsoever you have in doing any of our tasks after this, or indeed trying to apply this to your own data. Please do get in touch with us. Okay, so for the FTSE 100, I did 5 and 1,000. So somebody's asked me, how do you choose these values? Typically, I try and choose the upper value so I get 0 change points. So if I don't get that initially, I put it back in, and it in the next version of changepoint, you will be having something so it doesn't actually have to rerun everything that it's already done. But at the moment, it will rerun everything. So here there's a maximum of 225, and it actually only did 207. I then do my diagnostic plot, and you can see there's this absolute cliff here. Okay, and so these I would say are true changes. Now the question is, where is the elbow? I would say it's somewhere between these two red lines. Again, it's up to you. If I would look at the segmentation for this red line, look at the one for this red line, see which one I preferred. There may be an argument to take something in between as well, but ultimately it's not clear. Okay, so if I do this red line here, that corresponds to 11 changes, and the other red line is 34. So if I look at 11 changes, this is what it looks like. So you can see that the outlier here has been taken by 2 change points in very quick succession. That's quite common. When you leave the default penalty value, the outliers will be detected like this. And then if I move on to 34, then this is a segmentation. So between the two, I'm not really moving them, I'm just adding new ones, and you can argue which one. I'm not an economist, so I can't say one or the other. Okay, but you can clearly see that you're getting the most largest sets of changes, so you clearly get the crash here, and this was .com bubble here, you've got this outlier here, and you can correlate these with governments. With the heart rate data, then if you use the same options that we had before, then you get 33 changes, and this is the changes that are on the plot. I find these harder to read because you're looking at changes in distribution, so I sort of see, well, okay, I can see the distribution of this data here has a lower mean than this one up here, but in between, personally, I find it a bit more difficult to justify where changes are, because mentally I'm looking at the mean or I'm looking at the variance, whereas this is looking at a whole distribution. But maybe if I work with non-parametric data a bit more, I might be a bit more confident about this. So again, you can run it using crops, 91, but it only does 84, and then you can decide based on this. So this is more of an unclear, there's definitely a cliff here, but where you get to this plateau is less clear because it's more of a sloping instead of an actual bigger elbow. But around here, there seems to be a little bit of a lull in terms of this bit here is a bit flatter than previously, but then it does again have a big jump here. So I would either go before that plateau or just after. And that's either 11 or 15, so that's 11, and then there's 15 there. Again, they don't move very much when you add the changes in. So just to sort of finish the tutorial off, I'm just going to talk about assumptions. So all the way through this, I've been talking about, well, if you're looking for a change in mean in normal data, or if you're looking for a change in variance, or change in mean and variance in exponential data. But how do I decide whether the assumptions that I've made are appropriate? Okay, so I'm just going to talk about a likelihood ratio test for a change in mean now. So you're assuming that the data points are independent, so you're saying there's no correlation. They're normally distributed pre and post change with different means, and that there's a constant variance across the data. Okay, and so the question is, how can we actually check these assumptions? And the first thing is, you can't actually check these prior to analysis. So if I go back to my original data set M1 that we used, I have a single change point at time point 100. Now, if I look at, first of all, the histogram of that data, so I want to see, is it normally distributed? You can clearly see it's bimodal, and of course it's going to be, it's got 2 different means, okay? So looking at this, that is definitely not normally distributed. And so I'm trying to motivate here why you can't check assumptions prior to analysis. If you do the checks, they both come as no, it's definitely not normal. Shapiro-Wilks test here and the Kolmogorov-Smirnov test. If you look at the ACF for independence, now this data is actually independent. Every time point is independent from the previous time point. But if you look at it, it looks like long memory. Okay, you've got high autocorrelation that doesn't really dampen down. Okay, this is a feature of change point analysis in the sense that the change point induces this type of stuff. If you're interested, I've got another package that looks at the difference between change point and long memory processes. I can talk to you about it over the break. So in reality, what do we have to do? So what we tend to do is there's two options. You can check each segment independently and see if each segment satisfies the criteria, or you can check the residuals. So say you're fitting a mean model, you can subtract the mean, and therefore you should have normal random noise, white noise. Okay. So to check each segment independently first, I'm going to create a variable here called cpt.seg, and basically I'm going to take the change points from my data, I'm going to add on the 0 at the start, and then to that change point list. Okay, so this gives me just the change points in my data. I'm adding 0 onto the front of it, just so that I can look at that first segment more appropriately. And then seg.len here, I'm then having the length of the segments next to it. Okay, this is so that I compare 0 plus seg.len is my first segment, and the first change point plus seg.len2 is my second segment, etc. Okay, and you don't have to do this, but I'm just going to take out the data here, mainly just so that this actually all fits on one slide. And then I'm just creating a function here called Shapiro, and this literally tests. I put in my data set, my segment of data, and I'm testing here my data between the two. Okay. Strictly speaking, that should have a data argument. Now, that's really bad practice. I'm very sorry. And then I'm just returning my test statistic and the p-value. And then I can just use the apply function to basically apply the Shapiro function to my segments of data. Okay. And that just gives me, it's only got one change point here, so you've only got 2 segments, but when you've got more than that, that really saves you a lot of time. Okay. Again, I can do the same style, but with a Kolmogorov-Smirnov test. And again, so here, this one is marginally significant here if you use 0.05. And again, on this one, ironically, the one that is significant here is not significant in this one, so you can argue between the two as to whether it's normal or not. If you do some QQ plots, again, you can just use the apply function, and you get the QQ plots, and now you start to see why this one maybe isn't normally distributed because it's coming out in the tails. This one looks pretty close here. Okay. Again, you can do the same thing with the ACF, and you get the ACF for each one. They both look pretty independent at this point. So we've gone from highly dependent data just with one change point in to independent data when you take into account that the change point is there. So, you know, you might want to relook at some long memory papers. Then if you're looking at checking the residuals instead, so that basically is just taking your original data and you're minusing, you can actually use the repeat function here to repeat the means, the number of segment lengths. Okay, so that just creates an n-length vector with the mean, with the piecewise constant mean in it. Okay, so if you're not sure how that works, just do it step by step on some examples. And again, then I just need to run one Shapiro-Wilks test here, and it's not significant. And same thing with the Kolmogorov-Smirnov, it's not significant. So we say that the residuals are normally distributed. QQ plot, again, looks to be fairly normally distributed. And I'm looking at the residuals to say they're not correlated. Okay, so that sort of shows that the assumptions that I've made seem to be valid. Okay. So there's another task here which I'm going to leave you to do in your own time, which is checking the assumptions on the real data, so the Nile, the FTSE, and the heart rate that we've used. Using either segment or residuals, yeah?
Well, it's just a question. I mean, one thing is, it's of course nice to take these assumptions, but how important are they? I mean, we teach our students linear models. Observations come from a normal distribution with constant variance. It doesn't really matter.
Yeah. Well,
what matters is that they're independent.
Well,
how sensitive is all this to...
Yeah, I fully agree with you. The key one is the independence. So if you're using binary segmentation, then that independence assumption is really crucial. If you're using Pelt, less so. So you can actually see that because it's using an exact test statistic, because it can move the change points relative to other change points, it actually can cope with quite high dependence and still retrieve the right changes. But ultimately, I have seen many examples where the change point package has been used in the non-statistical literature where their assumptions are completely violated. They're fitting a flat mean to something that has a trend. And so this is more why I'm including this, in the sense that maybe if I include this, somebody might at some point check their residuals. But I agree with you, the normality assumption maybe is less important. But the dependence assumption is really crucial if you're using binary segmentation, less so if you're using Pelt. And so I've got a little consolidating task, which is, I thought might be quite fun for people. So once they've finished coffee, maybe they might want to have a quick try at this before Toby's second half. And so you can download the TV ratings for these 5 shows. Unfortunately, IMBD does not allow screen scraping. There is a package available on GitHub if you want to use that instead. And what you can actually do is you can look at the change points in these and you can predict which shows have been cancelled. And it's pretty obvious why some shows were cancelled if you just from looking at the ratings information on IMBD. So there's some references. These are just for the first half. And just to say that there's a lot of development in this area at the moment. So the robust change point detection is currently on GitHub, and Toby informs me it's on RForge as well. That will currently be coming soon by the end of the summer to the changepoint.np package. We've got join pin regression, which is where when you have changes in trend, you actually have to join the lines. That will be coming soon. FPOP again, Toby was involved in that one. So that's faster than binary segmentation, but exact. Again, that's on GitHub and RForge, but it will be in the changepoint package again soon. An online version of the Pelt algorithm will be in changepoint.online, again by the end of the summer. And if you're looking at doing multivariate data, then I believe there's one current approximate package available in R. We'll be adding our dynamic programming to the offering. And as I said before, if you're interested in looking at whether your data is long memory or a change point, because they can be very easily misconstrued, then do contact me as well, because I've got a package on that. So thank you very much for the first half. Please enjoy coffee and then come back for Toby in the second half, talking about supervised change point detection.